Hey everyone, my name's Jacob and I developed the Kaboom kit. And in this video, we're going to have a look at what's in the Kaboom kit. I'm going to give some quick directions and instructions so that we can get a Kaboom pretty quickly. And then I've got a more extensive lesson plan where it would be helpful if you had the work booklets, and we'll learn more about what's actually going on. So we're going to look at the science behind the Kaboom. So hopefully you've got a set that looks something like this, or you'll have enough components that you'll be able to do the Kaboom with. And so it's a beautiful little plastic case. Yours might be the same colour or not too sure. There's a foam infill that Tiny Science Lab actually laser cuts ourselves, or at least this one we did. Maybe in a few years' time other companies will be doing it for us, I don't know. And then there's a 5mm plastic syringe. Now 5mm plastic syringe, very good. This is called the plunger and goes in and out like that. And you can draw up water, you can push water out. But quite interestingly, and we might look at this later, you can actually have a chemical reaction in there that produces gas, and you can actually measure the amount of gas produced. So very, very interesting. You'll need a Bunsen burner igniter. Now we use these to light our Bunsen burners. We've got a little piezo crystal, and if you look down the end while you're clicking it, you should be able to see a little spark. Okay, so it's a little sparker. I don't know if you'll be able to see it on the video, but let's have a look. Let's see if you can see a little sparker. I think you might be able to, you know. Then there's some magnesium ribbon, and there's a vial of citric acid. Now this citric acid is commercial citric acid. We don't recommend that you taste or eat this. If you want to taste or eat citric acid, go to the supermarket and buy some in the cooking aisle, and you can taste that. Then we've got a 10mm conical flask, and inside that there's a little plastic spoon. Now that's actually a 0.25ml spoon, just for your interest. And isn't that a cute little conical flask? I love it. So if we put it back into the container, that will help it stay safe. Now I've got a pair of safety glasses. You should have a pair as well. They never, they never wrecked a good experiment. Just like a life jacket never wrecked a day on the boat. And I like boating, and that's true, you know. One other thing you're going to need to get an explosion happening is some water. Now I've just got some in a little beaker here, but you can have a little glass full. So the quick instructions, let's get into it. Firstly, you're going to need to put some safety glasses on. Ta-da! Get your conical flask out. Okay, get your conical flask out. And we're going to put 2ml of water into it. So I'm going to draw up a little bit more than 2ml. And then I can actually squeeze out until I get to the 2ml mark. Now it doesn't have to be 100% accurate, but that's 2ml, approximately 2ml is perfect. And just give that a little bit of a swish, and just feel out of interest, just feel the bottom of the flask. Now it feels slightly coldish, but not that cold, sort of pretty close to room temperature actually. Then you're going to need 2 tiny spoons of citric acid. 2 tiny spoons of citric acid. Now when you remove the lid, just sort of twist. Don't just sort of like go pull and it, you know, all the citric acid goes everywhere. Just sort of do it a little bit gently. Wiggle. Come on, wiggle. There we go. That way you don't lose the whole lot over your table. And I'm going to put my little spoon in, move it around a bit, twist it around, and there's 1 spoon. And it should be a little bit like cooking, and that is, you should be using like level spoons. Oh, some just went flying. That's not too much of a drama. Okay, now let's give this a swirl. Swirling, because what we're doing is we are dissolving the citric acid into the water. So that's quite important, that citric acid is dissolved. It's not melting, it's disappearing, the citric acid is breaking down into smaller and smaller and smaller particles, and so they're disappearing. So there we go. I've got a solution of citric acid in water there. And if you put it on your skin, you'll actually feel that it's a little bit colder than it was before. Now that's quite surprising, I can assure you. That's actually called an endothermic reaction. Okay, then open up your magnesium ribbon, and there's 20 centimeters. Okay, there's 20 centimeters of magnesium ribbon, and some of the pieces are broken up, but it's sort of folded into 2 centimeter lengths. Now, just get one of those lengths. You might need to break them apart. Okay, we actually like measure out 20 centimeters and then fold it up 10 times. And some of the pieces break, but some of them don't. And so just get out one length, which is approximately 2 centimeters long, and you can fold that up. Now, if it breaks, that's fine. Okay, that's fine. Just put all the pieces into the conical flask, and straight away you can see it bubbling. Okay, it's actually bubbling. It's producing a gas. Now that gas is actually hydrogen gas. You're producing hydrogen gas. That's quite exciting, isn't it? Hydrogen is probably the simplest element, but it's a fascinating element because it's lighter than all the other gases, and so it's lighter than air, and so that means it like floats. And so the first airships were actually filled with hydrogen. But there's another property that we're more interested in, and that is that hydrogen is a flammable gas. Okay, so you're actually producing a flammable gas in here. And if you put your finger on the top, you can actually feel something pushing up against it. I'm actually starting to feel some pressure, because as that hydrogen is formed, it's a gas and it's tiny little particles, and they're zipping around on the inside, and they're actually colliding with my finger, and they're pushing up on my finger, and that's called pressure, gas pressure, like bursting out. Now, if I put like a rubber stopper in there firmly, the pressure can actually get high enough that it actually shoots out the rubber stopper. Now, notice I haven't included a rubber stopper in this set, because if you think about it, what happens if a rubber stopper shoots out and it hits someone in the eye? It might cause injury. So that's why I didn't include a rubber stopper, because safety is very, very important. All right, now what you'll also notice is that it's not cold anymore. It's not cold. It's actually starting to warm up. It's actually an exothermic reaction. All right, are we ready? Get out your piezo clicker. Now, I have to swap fingers because I need my right hand here. And if you hold the clicker between two fingers like that, you should be able to put your thumb on the top. Now, have a practice at doing that, because if you can't do that, then you need to get someone else to help you. Okay, so you have to be able to click it with confidence. Now, I'm going to do this fairly quickly in a moment. I'm going to insert the igniter, but I'm not going to get it wet. We don't want the bottom of the igniter to get wet under any circumstances, okay, because then the spark won't work. So I'm going to go about halfway down and hold it at an angle. And let's see if we get a kaboom. We might not get one straight away, but I'm sure we'll end up getting some, or we better at least. Let's go. Here we go. And, ooh, there was a tiny little pop. Very, very small. You probably wouldn't have heard it, okay, but I heard it. That's okay. You might be thinking, oh no, what a dud. No, you just be patient. Just be patient. Let's build up a little bit more hydrogen, okay? All right, are we ready? And I'll go again. Whoa, whoa! I tipped it over. It's a boom. Okay. I got a bang. I got a kaboom. Ew. Oh. Let's see if I can get another one. I've tipped out half of my citric acid solution, but I can still see some reaction going on in there. Let's try again. Woo! Oh, I got a bit of a flame, and I got a small pop. I got an explosion. Definitely a kaboom. Now notice that I'm trying to hold my hand at an angle because if the flame comes up, if I don't have any part of my body above it, I won't get burnt. Now if you do get, feel a bit of heat or something like that, then just go put your hand under cold water. Okay, whenever you get a burn. Now I'm not giving medical advice here, of course, but whenever I get a burn, I always run under cold water. And woo! Yay! Now I've sort of I've practiced this a few times, although it might not look like it, of course. And I think from the 2 spoons of citric acid and 2 centimeters of magnesium and 2 ml of water, number 1, it doesn't get excessively hot, and number 2, there's enough reaction so that you can do 10 kabooms. That's what. Woo! There we go. Now I've tipped out half my solution, so I'm not going to get 10, but I am going to get quite a few. That was 3. Oh no, that was definitely that one wasn't so good. But look on the inside of the flask. I can see all these little droplets, and they're actually droplets of water. So the explosion, yes, it produces flame, it produces heat, it produces sound, but it also produces water. Isn't that interesting that an explosion produces water? Okay, well, let's see if I can do one more. Woo! Oh, that was like a much higher pitched, the typical pop test for hydrogen that Year 7 science teachers love doing with their students. Anyway, so that is the quick instructions. Okay, that's the quick instructions. There we go. All right, so let's get into the learning activities. So a molecule of citric acid contains 6 carbon atoms, 8 hydrogen atoms, and 7 oxygen atoms. And so the formula is C6H8O7. That's a molecule of citric acid. Now, what does it look like? What does citric acid look like? Well, I'm going to put some onto the little plate. I'm going to tip some out. And it's crystalline. That's the first thing that we should notice, that the citric acid is quite crystalline. And the crystals look about maybe 0.5 millimetre by 0.5 millimetre by 0.5 millimetre. They're fairly large crystals. And they're white. And they actually look quite cubic. Now, some of those are sort of like broken into smaller pieces. But it's definitely a white crystalline substance. And so the elements that are in it that make up the molecule of citric acid are, of course, carbon, hydrogen, and oxygen. All right. Now, I'm going to put that 2 ml of water into the conical flask. So let me just get 2 ml of water like this. Let me get a bit closer. There we go. 2 ml. And I'm actually going to, now you don't get a thermometer with this particular set, but you might have access to a thermometer. And these little digital thermometers from Tiny Science Lab are phenomenal. And so you get the probe, and you put the probe into the water. Now, 2 ml of water is actually not a lot. So I actually have to try and push the probe so that it's sort of like covered with that small amount of water. But I think I've been able to do that. And so we'll actually be able to see what the temperature is of that water. Now I'm trying to cover the probe as much as I possibly can. And will the temperature go down, or is that just the temperature of the water in the in that flask? I think it is actually 26.4. or 26.5. So it is, it's around the 26.5 degree mark. Then I'm going to just feel it. Actually feels a little bit warm. So it's actually slightly warm because I used this conical flask just a few moments ago to actually do that experiment, and the experiment actually heated it up a little bit. But that's actually probably pretty good, you know. Now I'm going to get 2 spoons of citric acid, 2 spoons of citric acid, pop that in, And just pop the lid on. And I'm going to give it a swirl to dissolve it, but I'm going to put the probe back in. Okay, I'm going to put the probe back in, and let's see what happens. Let's see what happens to the temperature. The temperature is now, remember it was 26.5 degrees? Well, now it's going down. I can actually see it going down. Look at this, we can watch the temperature going down. See this? The temperature's going down, 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 down. We're at 24.5. We go down further. Come on. I'm sort of, yeah, there we go, 24.4. And so 24.3. It's getting colder. What that means is that it's actually absorbing, whatever is happening here, the dissolving of citric acid is actually absorbing heat from the water. It's absorbing heat from the water, and that's causing the temperature to go down. It's what we call an endothermic change. Okay, an endothermic change. Now, I'm a little bit surprised because, well, I'm not surprised, but you could be a bit surprised because you might have thought that all chemical reactions produce heat, you know, when you burn things and explosions and stuff like that. But no, I mean, a lot do, don't get me wrong, but there are a few endothermic ones that actually absorb the heat and the temperature of the surroundings drops, okay? Now, the water is the solvent. Okay, so what's the solvent in this particular case? The water. What's the solute? What is getting dissolved? Well, that's the citric acid. And so the solution is citric acid dissolved in water. Okay, so we've got citric acid dissolved in water. Now we can have a look at our magnesium ribbon. Okay, so I'll just pop that there. I'll pop this back in here. It's good to try and keep things nice and neat. Always good to work neatly in science. And I'm going to pop out some of my magnesium ribbon. And what's the physical properties? All right, what are some of the physical properties? What can I observe about the magnesium ribbon? Well, it's silvery. Okay, it's silvery. It's shiny. It's actually lightweight to the touch. It's actually quite bendy as well. And so that the scientific name for that is actually malleable. Okay, and so magnesium is a metal, and metals have a certain number of properties in common. And so metals are good conductors of electricity. They're good conductors of heat. What else are they? They're malleable. That means that you can hit them with a hammer and they'll like spread out. They'll go flat. They're ductile. That means you can pull them into wires. And they're silvery when freshly cut. Now, mercury is a metal at room temperature, but it's a liquid, and so it's not malleable and it's not ductile, and you can't cut it. But if you cool it down a little bit more and it solidifies, then it does all those things. So there you go. All right, so I'm going to fold that up. I'm going to fold this one up, and I'm going to put on my safety glasses and pop that in there like that, the magnesium ribbon into the citric acid solution, and I'm going to make some observations. And I can see some bubbles, very, very small bubbles forming fairly quickly, and I can actually hear them. I can hear the gas and the bubbles, and feels a little bit like that sounds like that pop rock stuff that when you put it on your tongue and you feel hear the little explosions, it actually sounds like that. Then you will notice that the bottom of the beaker, or the bottom of the conical flask, I should say, will warm up. It will heat up. Okay? It might take a little bit longer, but as it warms up, and I can actually show you that. Remember it got down to 24.5 before? Something like that. Went down to 24.5. Well, if I pop this probe in, let's see if the temperature goes up at all. That's a good question, isn't it? Whoa! Whoa! Look at that! It's going up all right. 38. It's very exothermic. 39.8, 40 degrees. It's an exothermic reaction. And as it gets hotter, the chemical reaction actually goes a little bit faster. Okay, the chemical reaction goes a little bit faster. Now, if you're ever going to smell something in science, you never put your nose on what you're smelling. You always waft the smell towards your nose, just very, very gently, because it might be a very strong smell, might be dangerous. And so if you just waft a little bit, then it gives you a sense of what it might smell like. If this was chlorine gas, it'd be very dangerous to put your nose to it. Actually, probably fairly dangerous if that much chlorine gas was being produced. But thankfully, this is hydrogen gas, and it's actually feeling quite hot. Okay, it's actually feeling quite hot. And as it heats up even more, the reaction goes even faster. Now, notice also that the magnesium ribbon is actually getting quite silvery, and it's slowly disappearing. Okay, so eventually the magnesium will disappear, and then that will be the end of the chemical reaction. Or you might run out of citric acid, and then that's the end of the chemical reaction. So what are some properties or signs that a chemical reaction actually occurs? Now, chemical reaction is when a new substance is produced. Now, the new substance being produced here is hydrogen gas, but often some signs of a chemical reaction include light given out. So if something's burning or there's an explosion, sometimes you'll have light that is given out. A temperature change, so it's sort of like a dramatic temperature change, a lot of heat or given out or a lot of heat absorbed. In this case, it's a lot of heat given out. Okay, a lot of heat is given out. Or a gas produced. Hydrogen's being produced in this reaction. But if you add citric acid to bicarb soda, then the gas produced is carbon dioxide. So different gases are produced in different chemical reactions. A precipitate forms, that means a new solid forms, or a solid disappears. Now, in this particular case, a solid is disappearing. And then a final example of a chemical reaction is that there's a colour change. Okay, there's a colour change. So now metals generally react with acids to form hydrogen gas. Okay, so a metal and an acid forms a hydrogen gas and a salt. Now in this case, it's magnesium reacting with citric acid to form hydrogen gas and magnesium citrate. Okay, magnesium citrate is the salt. Okay, and it is a type of salt. The reactions come to a completion here because all the magnesium has, basically all the magnesium has been used up. Okay, so there we go. And again, this is an exothermic reaction. Heat is given out. Turn the page again. And explosion. So the piezo Bunsen burner clicker. Now all my gas is gone now. This is not going to react. There's not going to be any hydrogen gas because the hydrogen gas has floated away. I've been talking too much. And so I've got to pop some more magnesium ribbon in. I'm assuming that there's still some citric acid dissolved in there, and I haven't used up all the citric acid because it is using up the citric acid as it reacts. And so as the citric solution becomes more dilute, that will cause the chemical reaction to slow down, all right? But interestingly, the temperature of it, the higher the temperature will cause it to speed up. But I can sort of see that there's not much reaction happening there at all. So I might just tap in just a little bit of citric acid, just so that I can get a reaction occurring again. Now it won't take long at all because that citric acid will dissolve very, very quickly because of the higher temperature, and I can hear the gas and I can trap the hydrogen. And so we're going to do a kaboom, and the reaction is hydrogen plus oxygen produces the energy or gives out the energy, but it also produces a waste product, and that waste product is water. So here we go. Will it? Whoa! How good was that? Kaboom! And I can see water formed on the inside. And so the chemical reaction for that explosion is actually hydrogen plus oxygen produces water. Hydrogen plus oxygen produces water. And I'm actually going to show you the reaction using these molymods, or these little, they represent the molecules and the atoms present. So we started with hydrogen gas. Now hydrogen actually exists as what we call a diatomic molecule in the air around us. Now there's not a lot of hydrogen in the air around us at all, but there is a lot of oxygen. Got to be thankful for that, because otherwise we would not be able to breathe. The air around us is about 20% oxygen. So 20%, or 1/5 of the molecules in the air around us are oxygen. Here we go, and if I go like this, well actually, you know, a better way for me to show you the oxygen is not with those tiny little connectors, but in actual fact with slightly longer connectors like this. This is more accurate. Whoa! That oxygen's just escaped. Oh, there's more oxygen on that side of the room than there is on this side of the room now. Okay, so I've got a oxygen molecule and a hydrogen molecule, but it's a little bit tricky. There's something a little bit tricky involved, and that is I actually need 2 hydrogen molecules for a balanced reaction here. Okay, so I need 2 hydrogen molecules for a balanced reaction, and H2O, and let's go like this. Okay, so here we go. How does this actually work? Well, there's hydrogen produced by the reaction between the metal and the citric acid, so that's the hydrogen. Now, there's trillions of them. That's like millions and millions and millions of them. I've only got 2 here, so I really should say 2 trillion of these react with 1 trillion of these, but we'll just simplify it down. We'll say 2 hydrogen molecules are bumping around with the oxygen. Now they're not quite bumping hard enough for the reaction to occur. Okay, it's not like just exploding here all by itself. We actually need to give them a little bit more energy, called with the Bunsen burner lighter. Give them a little bit more energy. That speeds them up a little bit and gives them enough energy. Whoa, come back here. Enough energy where they break apart. So all of a sudden the particles, the molecules are breaking apart. And it takes energy to break them apart. Okay, it takes energy to break them apart. But when they reassemble and produce a new substance, okay, they actually give out some energy. Okay, so when they reassemble and form new bonds, they're actually then going to be giving out some more energy. So I'll get rid of these 2 bonds here, and replacing them with shorter bonds. But interestingly, have a look at what we're left with. We're actually left with 2 molecules of H2O. 2 molecules of H2O, and that is water. So we started off with hydrogen, or 2 molecules of hydrogen, 1 molecule of oxygen, and we ended up with 2 molecules of water. The explosion produced water. Now doesn't that just like blow your mind? Absolutely blows my mind. But I'm going to show you something else that's going to blow your mind, okay? Because this is very exciting, and I've got one right here. Look at this complicated thing. And firstly, I'm going to show you that there's some batteries. There's some batteries here. These are just AA batteries, and I'm now going to connect them to this little unit here. Okay, this little unit here, and it's like a 2 layers of plastic, and inside are these little tiny metal grids. Okay, little tiny metal grids, and something very special is actually happening right now that you can't see very well. But that electricity is splitting the water into hydrogen and oxygen. That's right, it's actually taking the water, and it's actually breaking apart the bonds, right? And it's sending hydrogen to this tube, and it's sending the oxygen to to this tube. And so I'm actually building up some hydrogen gas here and some oxygen gas here. Okay, it's not a fuel cell, but it's very, very similar to what we call a fuel cell. The fuel cell is actually here. This blue thing is a fuel cell. And what's going to happen in a moment is hydrogen gas is going to come in there on that side. Oxygen gas is going to come in on the other side. And it's going to combine the hydrogen and oxygen gas, and it's going to form water and another thing, electricity. And that electricity, I'm hoping, is going to run this motor when I turn it on. Okay, so that's what I'm really, 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 really hoping. I'm hoping that when I remove these batteries, I can get that motor to run using the hydrogen oxygen gas and this fuel cell. So firstly, I'm going to pull the battery out. So let me try and get this battery out. Oh, come on. Maybe I should have, oh, there we go. One battery, gone. And now this is not magic, by the way. I'm not like, this is science and there's no magic tricks involved. There are no batteries. There are no batteries in this unit at all anymore, okay? I absolutely promise. I'm not trying to trick you, but I'm going to turn this, oh, what? Come on. Come on. Oh, hey! I had to get the gas flowing. Look! Look! I've got a voltage there. I've got electricity. Hydrogen and oxygen gas are being turned into water. Drop, 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 drop. And electricity. Is that not exciting? Now, I think I can actually pop this up here. I think there's enough gas in there to run it for a little bit. So I'll just pop that. Oh, just got some water splashed on me. And there we go. Can you feel the air? Can you feel the air blowing onto you? How exciting is that? And so I've stored the electrical energy in the hydrogen and oxygen gas. How good's that? Also, what's really exciting is, yes, I used batteries to produce the electricity, but what if I used a solar panel? What if I used a solar panel to produce the electricity, and I split the water and I stored it as hydrogen and oxygen gas, and I could produce the electricity nearby, or I could even send the hydrogen and oxygen gas down a tube, or I could store it or down a pipe, I should say, or I could store it. I could store it in a tanker, and I could transport it like that. If I use solar power, then this would be clean energy, okay? Clean energy. And the only waste product is water. Now, if that doesn't excite you, I don't know what will. So, I love it so much. Also, what I've always found so super exciting is these barbecue clickers. A little click and you make electricity. You're actually flexing, putting pressure on a crystal, and when you put pressure on it and there's some movement, it actually generates electricity. Or alternatively, if I put electricity in, I can actually cause it to flex. And so that's actually one way to make a speaker, a little piezo speaker. Now, I use this spark to give the molecules a little bit more energy, just enough energy so that they bump into each other, and that causes them to break apart. And then when they form the new bonds, the kaboom, the energy is given out. Well, that's it for the Kaboom kit and a little bit of a deep dive into it and the different components and that sort of thing. Hopefully you understand it a little bit better. There was one other little thing I was going to show you, if you remember. Okay, I'm actually going to do where I'm thinking, what am I doing here? I'm going to tip that in there like that. I'm going to get some citric acid in here, and now that citric acid is technically the same as what you buy at the shops, so in the shopping aisle. So if you do run out, you can replace it with citric acid from the shops. So I'm just dissolving that. And what I'm going to do is going to pull out my plunger out of my syringe. I'm going to get a small piece of magnesium ribbon, in fact, just like 1 centimetre, so not very long at all, 1 centimetre. Pop that in, push that plunger in, so I've actually got some magnesium ribbon in the, I can't get the water out like that, so I'll tip that little beaker out, not the water, the citric acid I should say, and I'm going to draw up some of the citric acid, and I'm going to put my thumb on the end of the syringe, okay, and do you know what's going to happen? That gas produced is going to push that syringe up. Okay, the syringe will go up as long as you're pushing with your thumb to stop the gas coming out. So that syringe will go up. And chemists, so scientists who study chemistry, can actually do lots of experiments where they can work out how much gas is produced for a particular amount of reactants. You know, how much gas is going to be produced for, 0.05 grams of magnesium. Okay, well, I think the syringe is going up. Is the syringe going up? I mean, it goes up slowly. But I see a gap. I see a gap above it now. So it's definitely going up. Now, if I take my finger off, then the liquid will get pushed out by that gas. I'll show you. If I take my finger off, in fact, what's happening now is that the gas being produced is causing the liquid to push out. But I've actually got some hydrogen gas trapped in there. So that is very, very exciting, isn't it? Anyway, hopefully you've enjoyed this lesson. I look forward to seeing you in future courses or future lessons where you have some other Tiny Science lab equipment. Okay, the answers sheets are going to come up in a moment, and I look forward to seeing you soon. Bye for now.